we have seen to solve quadratic equation ax squared plus bx plus c equals 0, when there's a special case, c equals 0, there's a factoring technique. It works by factoring ax squared plus bx into ax plus b times x. So for this quadratic equation equals 0, we know that one of the term x plus b, or x, has to be 0. So that we get the two solutions for x for this quadratic equation, and these are the only solutions for the quadratic equation. In this lecture, we're going to generalize this approach to solve many quadratic equations, even when c is not 0. Remember that for this factoring technique, when c equals 0, the key for it work is we are factoring 0 equals ax squared plus bx into this x times ax plus b, right? So now the wishful thinking is when c is not 0, so we have this equation of ax squared plus bx plus c, can we still factor this into something like ax plus p and times x plus q? We know that we're not going to have an x factor, but can we have the x plus q factor such that this equals ax squared plus bx plus c? If this is possible, remember this is our thinking, if this is possible, then we solve this quadratic equation because of this key property. When I have these two terms multiplied together, this equals 0, then one of the term has to equal 0. And this gives the two solutions, and these are the only solutions for this quadratic equation. So in the following argument, we're going to derive this for many examples. But first, let's make a simplification. Let's assume a equals 1. And look at the example. Example 1. X squared plus 4x plus 3 equals 0. Now the trick doing this factoring is something called reverse engineering. Let's assume this is actually first feasible. So x squared plus 4x plus 3 is going to equal x plus p times x plus q. And if this factoring is possible, then we know the solutions is going to be x plus p equals 0, x plus q equals 0. But assuming this works, we're going to derive or back out what are the properties of p and q, and to see if we can just eyeball them and get them, easily. So in here, we say if we assume that it's equal x plus p times x plus q, let's multiply this out, expand this out, and compare the coefficients to the x squared plus 4x plus 3, which we know, right? So this, by doing the FOIL, you take this x times x and x times q and p times x and p times q, we expand. So this equals x squared plus qx plus px plus pq. Now we're going to simplify this expression by combining the terms with the same signature, or someone called the like terms. This equals x squared plus p plus q x plus pq. Now, if we compare this expression with this expression, we know that if the two expressions are the same, that means for every term, they have to be the same. So in here, x squared, they're already the same. But in here, 4x equals p plus q times x. That means p plus q is going to equal 4. And for the constant term, this is 3, in this side is P plus P times Q. So PQ is going to equal 3. Now let's look at P plus Q equals 4 and PQ equals 3. Can we spot simple solutions to this? And we're only going to searching solutions of P and Q, both integers. In here, you see that if P equals 1, Q equals 3, because 3 is a prime number, right? So there are only very limited factoring of 3. So 1, 3. Actually, in fact, there's only 1, 3, and 3, 1, and -1, -3, -3, -1. And they are symmetric. It's not affecting P plus Q. And the one solution that satisfies both is going to be P equals 3, Q equals 1. Now you say, how about P equals 1 and Q equals 3? Well, it does not really matter because it's symmetric. So this equals x plus 1 times x plus 3. Now we know that for 0 equals x plus 1 times x plus 3, this has to have either x plus 1 equals 0 or x plus 3 equals 0. So x is going to equal -1 or x equals -3. And these are the two solutions. Okay, so we actually use the factoring technique to solve a very simple quadratic equation with non-zero b, non-zero c. That's quite an improvement. Let's look at another example. Example 2. X squared minus 5x plus 6 equals 0. Now we're already pretty comfortable, so we assume that the x squared plus minus 5x plus 6 can be factored. So x squared minus 5x plus 6 equals x plus p times x plus q. Again, let's factor this out, but this is always going to have same form. So if you are getting, a little bit of exercise, you know that this is always equal to p plus q times x plus pq. And again, by comparing every term of the equation to both sides, you know that p plus q equals -5 and p times q equals 6. Again, we're only searching for solutions PQ such that PQ are integers. So for P times Q equals 6, this is the equation to searching possible candidates for PQ because the factoring has very limited choices, right? So PQ equals 6, you only have, 4 possible pairs, 1, 6, or 2, 3, or -1, -6, -2, -3. And you're going to take those possible candidates, plug into P plus Q to see if it satisfies P plus Q equals -5. This clearly not, this clearly not. When P equals 2, Q equals 3, P plus Q equals 5. So this is not. But P equals -2, Q equals -3, they add up to be -5. So this is the solution. So that means 0 equals x squared minus 5x plus 6 can be factored into x minus 2 times x minus 3 because p equals -2, q equals -3. Doesn't matter if we switch the order, does not, because this is kind of symmetric, right? If you take p equals -3, q equals -2, you still get the same factoring. At this point, we know they multiply together equals 0, so x minus 2 equals 0, or x minus 3 equals 0. So we know that x equals 2 or x equals 3. And this is the factoring technique to solve quadratic equations. And this is super useful for most cases, especially in contest or your final exams. You should be able to solve it using factoring technique. And the basic skill it uses here is really of factorization. So if you can exercise frequently how you factor this in your head, and then you can do this very easily.